Stop worrying about homework and start learning with confidence. This is Ask Learn. Complete help for every subject. Like, share, subscribe for daily learning videos.
Okay, so this problem, the setup that we have is that we have two straight wires, emphasis on the straight, that we are given the distance of, or the length of. We know that they have a length of L, and they have the same length. We are given the mass, M, for each wire, and they have the same mass. We are given the distance d between them. I will call lowercase d for our calculations. And we want to find what the current is. We're told that they have the same current. So we'll just for reference have them facing the same direction, which we're told they face the same direction, but we'll just have them facing to the right. So right-hand rule tells us for a wire with a current traveling through it that we point our thumb in the direction of the traveling current and our fingers will curl in the direction of the magnetic field. So for the top wire, our fingers will curl in the direction around the wire this way. And same thing for the bottom, so it will curl around that way. So we are told that the top wire is fixed in place and the bottom wire is floating, which is a good hint to us that it's being held up there by some other force. So we want to find the current. And we know we're probably going to have to use our equation for magnetic field from a current carrying wire. So we have our equation for that is B is equal to mu naught, the constant, times the current, which is good because that's what we need to find, so we have an equation that has our current involved, divided by 2 pi times the radius. So now what they mean by radius for this equation is how far out from the source of the magnetic field we are. So we can see, or as you can see, I have a circular path for the magnetic field drawn around the wire. So that's what this radius is here. It's the distance from our source, which in this case, from wire 1, let's name these wires for reference for the future. We have wire 1 on the top, and we have wire 2 is the floating wire. So the distance from wire 1 to wire 2 is d, which will be our radius for this equation. So now this is something that we can calculate everything for. We know everything other than I. So just for brevity's sake, I'm going to call all of that a constant c. I'm just going to call it c for this case, because we can plug in everything we know here. We have the radius, which is d. Plug that in for r. We know our constant mu, and we know 2 pi. So B, in this case, the magnetic field from wire 1 on wire 2, we can specify that, call it 1, 2, from wire 1 on wire 2, is equal to all of that constant, C, times our current. And once again, C is simply equal to mu naught mu naught divided by 2 pi r. So we have our magnetic field in this case. So we need to find, we don't have a number for it, we just have what it's equal to. So C is what we know. We don't know I or B. So we have an equation with two unknowns, which means we need another equation here. So a good start is we are given the mass. So we're probably going to have to use the mass to find something. And we know this wire is hanging. It's just, or this, I'm sorry, this wire 1 is hanging, wire 2 is floating. So we can calculate the force that would need to be, if there were no force, this would fall to the ground. So the force has to be canceling that of gravity. And the force of gravity, we know how to calculate. I'm going to call it F sub g. Force of gravity is mass times our gravitational constant. So we know both of those things. G, in case you don't remember, I'll write up here. G is equal to 9.8. This is acceleration. So this is in units of meters per second squared. So that's G. Just multiply that by the mass, and they have the same mass, so we don't need to worry about which one. So the force of gravity pulling this down is equally canceled by the force from the magnetic field. So we have a force here, and these are completely perpendicular, so we don't have to worry about an angle between them. Our force for a magnetic field with a current, let's give it an abbreviation also. We'll call it F sub B because it's from a magnetic field. F sub B is equal to ILB. Okay, now we're getting somewhere. But these forces are equally canceled because this wire isn't moving. If it had a velocity, then we would have to calculate the difference in the forces, but it's simply floating there, which means it's in equilibrium, which means these two forces are equal and opposite. So our force diagram would look something like this. We have our wire, which I'm just going to make a dot. We have our force of the magnetic field, F sub B, pulling up. And we have our force from gravity pulling down. And they are equal and opposite because it's not moving. So that's our force diagram here. So we can use our F sub G, which we know, in place of this F sub B, which we don't know. But we do now because it's equal to that. And this is a number we've already calculated, so I'm going to use F sub G here. We have a value for B, and we know our length here. So length is a constant. I'm going to have that be absorbed by your constant C, because we know what it is already. So B is CI, but we have another I here. So now this B becomes CI squared, because we have two I's. Now, you know what? Let's change this C. We'll change it to K now because it has another constant in it. I'm simply just using K to represent all of these numbers put together. So K is equal to what we have for C here, multiplied by the length of the wire. So that's what K is. It's this number. Whoops! It's this number we have for C multiplied by L, the length from this equation. So now we can find our current here because we know everything else. And we're going to have to take the square root because we have an I squared here. So the square root, we need to move the K over, so we have our F sub G divided by the constant K. This is all under the square root sign. And that will give you your current. And they both have the same current, so we don't need to worry about doing this for the other wire. And so just remember to plug in everything for your constants here. And that will give you the current.